My name is Andrea Herbst, and I'm researcher at Fraunhofer ISI in Karlsruhe for almost 10 years. My research strongly focuses on strategies to achieve a circular low-carbon EU industry sector. And together with my colleague Simone Zanoni, who is a full professor in industrial systems at the University of Brescia, we would like to warmly welcome you to our first session, in which we talk about circularity and decarbonization of the cement and building sector. So we know that cement is an energy-intensive and CO2-intensive product, which is used in large quantities as a building material, for example, in the form of concrete. But of course, due to chemical reactions, technical restriction, high temperature needs, the options to decarbonize this cement industry are limited to either CCS or fuel switch to biomass and secondary energy carriers, maybe also new binders. Thus, circularity measures in the cement and building industry can make an important contribution to reduce CO2 emissions and achieve a near carbon neutral sector. So today we have 5 presentations that dive into the aforementioned issues. And after each presentation, we have a short 7 to 8 minute question and answer session. So we would kindly ask you to put your questions in the Woover session question and answers, and please also add the name of the presenter you like to address with your question. So I think after this we can just get started maybe with the first presentation of Timo. And Timo is a 4th year PhD student at the University of Comillas, and he's working on deep decarbonization of the industry sector in combination with the energy system. He's also one of the co-founders of the Renew Industry Consortium, which is also part of the eceee network. And today he will talk about overcoming the carbon lock-in, especially for the Spanish cement sector. So Timo, the floor is yours.
All right, 1 second, I'll just time myself. Okay, Andrea, thank you very much for the presentation, and thank you for eceee for organizing this conference. Yeah, so the title of my presentation is Overcoming the Carbon Lock-in, a techno-economic analysis of the Spanish cement sector. And I'm actually going to use the cement sector to introduce a little bit the model of my thesis, which can also be applied to other industries. But let's first talk changing. Okay. Oh. Okay, it's a jumping slide, sorry. So when we talk about cement, we first have to talk about what cement means today. I mean, as introduced by Andrea, it's very energy intensive and very emission intensive. So today in Europe, we consume about 160 million tons of cement, which is about 310 kilos per capita. And by that, we emit 120 million tons of CO2, which is a carbon footprint of the EU. So where do we want to get there when we talk about 2050? First of all, emissions have to be reduced to a minimum to achieve, in case of Europe, the net zero emission goals. But then we also have to take into account, I mean, this is from a study here I quoted from Material Economics, that demand for cement services in the end will probably remain constant. So while this is the EU picture, I also want to introduce a little bit to the Spanish picture, because the Spanish picture is a little bit more extreme. And the Spanish picture, wait. The Spanish, you really have a delay in the presentation. It's really, okay. The Spanish picture can be basically represented by these 2 pictures. The first one is one of the many ruins that you see all over Spain, and which are basically the product of an aftermath of the real estate bubble that you had in Spain in the early 2000s. And basically you had a complete overconsumption of cement, which is currently resulted in these ruins that are not used. On the other side, you have the picture below, which is the brand new cement export facility of Heidelberg Cement at the port of Malaga, to basically export the overproduction of Spanish cement. So if we look at it in terms of numbers, this is the historic production and consumption of cement in Spain, and you can see that it peaked at 1,200 kilos per capita in 2007, which is 4 times today's average consumption in the EU. And one thing I want to highlight, that almost all of that production was, all of that consumption was covered by national production. So you have capacity for producing 4 times the cement in Spain that you actually consume in the EU average. And when we look at today's situation, you actually can see that reflected. I mean, today's the consumption is still much lower than the EU average, also at aftermath from that crisis. But on the other side, production is much higher. So you produce 60 million tons of cement per year, and about 4 million tons, 25% are being exported, and especially as a carbon-intensive material, which is critical to countries which are outside the EU. So, for example, South America. So how can we decarbonize the sector, or also the Spanish sector, European sector? We first have to talk about technologies. And when we talk about technologies, I'll try to keep it quick because there are other people that will talk more about it. In general, high temperature electrification is very difficult for cement. And as well as biomass, it only allows for partial emission reduction, because you can basically only reduce the energy-related emission reduction and not the process-related emission reduction. Then alternative materials are often in early development stage, and it's not really clear if they can actually fully replace them. And in the end, we only have carbon capture and storage as the only decarbonization option. But the big question remains what to do with all the CO2. This is a little bit based also on my own research. I put the paper here that I published about 2 years ago, which is reviewing cross-sector decarbonization technologies in the energy-intensive industry. But I would also like to highlight the work of another speaker of today, of Ida, who will probably talk much more about the latest publication about the technical roadmap in the cement industry of the Mistra project. So when we have all of these technologies, we have to ask ourselves, why are there no technological changes so far? When we talk about technological changes, we have to talk about economic feasibility. Because all of these options are not feasible, and all of our cement plants here in Spain that we have today are basically using very carbon-intensive processes today. So when we talk about economic feasibility, we have to ask, when do these alternatives become feasible? How can they be implemented? How can they be supported? And how especially the age structure of installations that we have in Spain right now favor or maybe disfavors the transition and makes us end up being in the carbon lock-in. So, and then the big question is, how will deep decarbonization change the sector in Spain? This question we try to answer by using a model that I'm developing right now, or it's under development. We call it transition towards industrial decarbonization. And it's basically a mixed integer linear programming model, which tries to optimize operation and investment of industrial sectors, energy-intensive industrial sectors, not only the cement industry, over the entire time horizon, for us right now, 2020 to 2050. It's a modular approach where we divide the processes in these industries in different standardized process operations. And as an example, for the cement industry, you basically divide the current process that you have in 4 different steps: mixing, transforming, forming, and milling. And this basically, in the end, allows us to model all industries in the basic materials sector. So how does it look in detail? It's a mathematical optimization problem where we basically try to minimize the total cost, which is the cost of installation, the cost of energy, the cost of materials, the operational costs, additional operational costs, and most importantly, when we have the EU ECTS, the cost of emissions. We sum all of that over the time horizon of 30 years, the different factory level processes that you have, or factory level process alternatives, the processes itself, and likely alternative that can be implemented by the model. When we look at the decision variables, we look at the energy and relate to the energy cost, the different energy types, the material that can be used, and for sure the emissions. And what I'm going to present you now, next slide, are the results of a very simple mock-up example where we said, okay, we have 30 cement plants in Spain. Each has 1 million tons of capacity, and average kiln line of these plants is 30 years. And what I highlighted here was, Andrea, I only have 7 minutes 30 here on my clock, not 12. anyway, so each plant, year one plant has to be renovated. And when we look at the EUTS development, we know the carbon budget for 2030 and 2050. So we can kind of assume that we have, with a gradual removal of free allowances, that the CO2 price will increase to 50 euros in 2030 and 100 euros in 2050. When we look at the Spanish demand, we expect a recovery of 20% until 2030, and then it stays constant. All the technology costs we base on literature for the moment. Well, the main focus here is on new BAT technology, best available technologies, and CCS options, especially integrated plants, and basically end-of-pipe solutions that you can additionally mount on best available technology processes, which have a lower emission reduction rate. So again, what I'm going to present you now, and I don't want to go too much in detail because there are some flaws in the graphs that we have because it's ongoing work. And with the first data that we have from the Cement Association, we are currently trying to fix that. But basically, what kind of results can you get? You kind of see how the different plants are being operated given demand and CO2 price scenarios. So here we see that first, the old plants are operated in the lower price ranges. And in that case, only half of the existing capacity is operated because you are only supposed to satisfy the demand. We completely quit out exports. These plants are basically retired prematurely, completely in the mid-20s. And then because of the rising CO2 price, you switch first to new best available technology and then equipment as post-combustion CCS. And then towards the end, you go and switch towards integrated CCS plants. Also early retire the existing installations when the CO2 prices reaches a range of more or less 90 euros. When we look at the cost, again, this graph is also not correct because one thing in these results that is not incorporated is the remaining installation cost that has to recover from existing installation. So again, there are some flaws in that, but you can kind of see how the model is by having new installations, try to minimize the cost of relative production that you have. But if you look at the benchmark price of 58 euros per ton of production today, this price is significantly higher and increases with increasing CO2 prices. It only gets a bit lower if you install integrated CCS, which is then, the model actually runs until 2100, is then basically compensated by the annualized cost. If we look at emission reduction, again, in the model we have very positive assumption about the emission reduction of 0.5 ton per CO2 per cement in the end. You can basically reduce emissions because the max capture rate that you have is 90% to 10% of the original one. So where do we go from here? Because again, this is a mock-up case and we are currently trying to work with the cement industry to make this a full scale with proper data. So we want to have case study data aligned with the Spanish Sector Association. Then we want to extend the scenario landscape significantly to see how certain sensitivities work on that. And then, very interestingly, we want to compare these results to model runs for other sectors, for example, steel industry, chemical industry, to basically see how different policies, which is another field of my work, policies on industrial decarbonization can actually affect the different sectors if the same policy is put, let's say the policy is put industry neutral, and we see which industry decarbonizes first. And this basically brings me to the end of my presentation. I always say decarbonization without deindustrialization. That's a little bit the motto of my work. And thank you very much for your attention. And I'm really looking forward to your question. And as Andrea mentioned in the beginning, we are founded as research network about industrial decarbonization half a year ago. And I would be really happy if some of you approach me afterwards and want to join and participate in that. Thank you very much.
Okay, thank you very much, Timo, for your presentation, and sorry for interrupting with our TikTok clock. So currently, I think this was a very interesting presentation, and I really think the cement industry is one of the most important industries to decarbonize, however, yet not the most innovative one. So you did look at the Spanish industry in detail, but your approach, could it be easily transferred to other European countries? Do you just need the information on the plant stock, or what is your next step?
I mean, exactly. That's exactly the point. We started with a Spanish case because we were approached by the Spanish Cement Association, so we really want to make it a Spanish case study first. But the idea is, especially if you look at a European policy instrument that work for all European operators in the same way, that operate in a single market, you have to feed with European data. And I mean, the question is just availability of data. To what extent do you simplify the existing plans that you have? Given on the data that is available. And what I think is actually the sweet spot of that approach is that you can in the end really compare if you have, for example, the cement industry, how it can decarbonize with, for example, the steel industry, when you have similar policy measures for the entire European context.
Okay, thank you very much. So Simone, do we have any additional questions?
In Wova seems no question right now. Let me check again. Okay. No, it seems clear. I have a question regarding the model, Timo. In the mathematical model is mainly different parameters related to each plant, to each cement plant. But what about consolidating the production in fewer places? This probably may also imply usage of different material coming from different quarry, or maybe also the transportation is influenced. At least what happened in recent year in Italy. We started with more than 100 cement plant here in Italy, and nowadays there is a third of that number of plants, so less than 30 plants nowadays, but with a higher capacity. So especially when you renovate the plant, might be useful to also increase the capacity, and instead of renovating a couple of different plants. But in that case, transportation plays a role, since probably you have to increase the transportation. What's your thought?
What the model currently works with, and as I said, right now we put it at 1 million tons, so the results are not very good in that regard. But what we work with is the current stock in Spain. So we really say, okay, so many million tons, that's roughly the age of the installation, that's when it has to be roughly renovated. So in that regard, you already, as you say, you start from a very segregated approach. And if you look at it from the modeling perspective, what the model does to make it easier, it basically always puts a plant in the size it requires in a certain year and adds up to the capacity. So if in year 2030 a new best available technology plant with CCS post capture is required, it adds one plant in the size it requires. So there is no geographical component into it. It might be interesting to add up to that. But currently what you're describing, the model by design forces to have big installations, and also there is no cost factor in basically penalizing small installations right now, but just the way it works, it puts big installations.
Okay, thank you very much for the clarification, Timo.
And I think
there is a question. We have a couple of minutes from Jean. Let me copy in the chat. Okay, let me copy here. Sorry, I cannot. Let me. It regards an aspect I can firstly read with respect to implementation of CCS. How is the question of transportation and storage of CO2 discussed in the Spanish context?
In the Spanish context, there is actually a very active platform which is trying to push for the technology, where you also have, for example, the cement, but also especially the refineries, because many Spanish refiners, Repsol, Cepsa, dedicated themselves to zero emissions in 2050, which actively pushes that technology. But the clear discussion that you have also in Northern European countries about where to store and the legal the legal implication of that is very much ongoing as well. One big advantage that you say, if you can say that you have in Spain, that the country is so big that you might have a little bit less not in my backyard issues with it, but I also see it very critical to what extent carbon capture and storage can be realized in Spain in that regard, because the public opinion is also not 100% favorable in that regard.
Okay, thank you, Timo, and thank you to Johan for his question. We have 1 minute left.
Okay, so I think we will now come to our second presentation, which is from Navdeep, who is working as an assistant professor in the Department of Civil Engineering at the National Institute of Technology, Jalandhar, India. And his research focus is on sustainable concrete and construction, utilization of coal combustion products, recycled materials, durability of concrete, and non-destructive testing. And today he will discuss the utilization of industrial and agricultural byproducts in blended cement mortars. So the floor is yours.
Oh, thank you so much. Good afternoon to everyone. Myself is Dr. Navdeep Singh. I'm working as assistant professor in Department of Civil Engineering. So this work is a collaborative work between my institute and Dr. Marlene Erin. So first of all, I would like to thank to her. So without you can say wasting any of the time, I'll directly going towards my topic. So utilization of industrial and agricultural byproducts in the blended cement mortars, creating an effort of the circular economy in the Indian cement industry. So next slide, please. I think yes. So I have divided my presentation into the following sections. So first of all, I'll be briefly talk about the introduction, then the research objectives will be covered, then what are the materials and methods we have followed, and then we will talk about results and discussion, and finally we'll talk about the conclusion part. So the rapid increase in the concentration of carbon dioxide has already fastened the process of global warming on this very planet. So as you know that almost 2.4% of the global carbon dioxide emission comes from the cement industry. So India is ranking at the second position throughout the world, as it is a projection that it is going to produce about 600 million tons of cement by end of year 2025, and by end of year 2050 it will be reaching more than 1500 million tons. So for last 2 decades, Indian government is quite aware of the you can say target, and they have set the target for reduction of the carbon dioxide emissions by 20 to 25% by the end of year 2030. So reaching decarbonization requires the joint efforts from the public sector as well as from the private sectors. So as you see the map of the India, you will be having there are almost 215 major big cement producing plants, and there are almost 850 small minor plants, and they are producing almost you can say 240 kg per capita cement every day. So Indian cement industry is targeting to condense the carbon dioxide emissions by around 0.35 tons of carbon dioxide by end of year 2050. So this is one of the plans or the strategies which Indian government has introduced. So adoption of low carbon technologies has also been you can say introduced by creating such kind of techniques like carbon capture and carbon usage and storage. So by this they have projected that at the end of year 2050 it will be saving about 212 million tons of carbon dioxide. So these are you can say the 10 most prominent industries which are creating or generating cements in India. So coming up to you can say the industrial byproducts scenario of industrial byproducts in India. So almost you can say India is a developing country, and there are huge amount of factories are there. For example, we have the factories for the coal combustion products are hugely generated like fly ash and coal bottom ash. Likewise, from the iron industry, we have the creation of the slag as well as we have the creation of the quartz. Then we have the from the copper industry, copper slag is generally created. So all these various kinds of industrial byproducts are generated from various industries. Next scenario is about the agriculture byproducts. So this India is also one of the countries which is directly whose economy is directly influenced by its agriculture sector. So you can see that in every year we have a huge amount of the byproducts generated from the agriculture residues. So approximately 362 million tons of the ashes are generated because these byproducts are generally burnt at the end of the reaping of the crops. Ultimately, this is one of the best methods, but this is one of the poorest methods for dealing the governments that how to create or how to stop such kind of the efforts. So there is no clear path for solving this kind of problem. So coming on to the research objectives, so very few studies are available for industrial waste and agriculture waste based cements or blended mortars, which highlights the reduction of the carbon dioxide emissions from the use of blended cements with industrial or agriculture wastes. So to overcome this observed gap, this contribution focuses on the performance of the blended mortars based on industrial and agriculture waste. So a generalized approach has been followed to estimate the carbon dioxide emission reductions through the use of these very of the cement additions or supplement cementitious materials, since all these byproducts act as the pozzolans, and these pozzolans are replaced with a certain amount of the Portland cement. So the study also evaluates the carbon dioxide intensities of different blended cements that are used with the with use of either industrial or agriculture waste. And finally, we have this contribution also sheds the light on the impact of the industrial and agriculture waste as clinker substitutes on the compressive strength, since compressive strength is one of the prominent factors for determining the overall performance of any of the mortars. So that is why we are focusing on this, and ultimately we are focusing on that how much carbon dioxide reduction will be there if such approach is going to be successful. So coming on to the materials and the properties, so we used for you have done, actually this work is basically experimental part, some part is experimental and other is a theoretical portion also. So in the base of the theoretical experimental part, we have used various byproducts generated from the industries. So by fly ash, which is a byproduct of the coal industry, then coal bottom ash, again it is the part of the coal combustion product. We have the granulated glass furnace slag generated from the iron industry. Then we have one more is copper slag generated from the copper industry. On the other hand, the agricultural byproducts are used at sugarcane gas ash. Then we have used the rice husk ash and corn cob ash. So if you go to that very of the chemical composition of these industrial and agriculture waste, these all are the chemical compounds related to that very of the PC. So that's why they are easily replaceable with the certain amount, for creating for generation of the specimens or for generation of the mixes. So this is the table which shows the replacement levels and the various mixes we have made. So for industrial byproducts, we have chosen a constant replacement level, that is 20%, and we have made the specimens. Likewise, for the generation of agriculture byproducts based blended mortars, 5%, 10% and 15% replacement have been made, and certain mixes were casted. So coming into the experimental program, we have done very basic tests so that everyone, not from the civil engineering background, but from throughout the world, one can understand about this very of the system. So compressive strength test, basically they check about the how much the toughness of the material is there. So that is why we have performed that very of the test. So basically in this cubes are casted of the specific according to the code or the specific size as by ASTM 109. Then we have done the calculations for the reduction of the carbon dioxide emissions. So a general approach has been followed, that creation of every ton of cement is going to create 1 ton of approximate 1 ton of production of the carbon dioxide. So based on that, we have calculated the reduction in the carbon dioxide. Now coming on to the results and the discussion. So if you see that in case of your industrial byproducts based mortar mixes, so we have done the curing up to 56 days, and also this work is keep going on for another 90 days. So here the results are up to only 56 days, that we have seen that at 20% replacement levels, not huge difference in the compressive strength has been followed. This means that the mechanical performance what we are proposing is found to be equivalent as that of the conventional mortar mixes or the conventional PC mixes. Likewise, we'll be having the creation of or the results for the agriculture byproducts based mortar mixes, where we'll be having the results for up to 28 days. So in this case, we'll be finding a significant reduction, but for the lower, you can say, the replacement levels, we have the less reduction compared to the control mix. So one can say that the best performance has been performed by the RHA based mixes, then for SCBA based mixes, that is sugarcane gas ash, and then for corn cob ash based mixes. So coming on to the carbon dioxide reduction or the calculation part. So if we are using per cubic meter capacity of the mix, then we have used 585 kg per meter cube of the cement initially, but after replacing of 20% with the industrial byproducts, we have reduced up to 115 tons of carbon dioxide. Likewise, for agriculture byproducts, we have reduced the carbon dioxide emissions by 5%, 10% and 15%. So subsequently, these values have been calculated according to the simple calculations. So as per projection, so this projection has been done by the government of India, where in by end of year 250, it is going to, you can say, create the 1500 million tons of the amount of the cement. So if we are replacing 20% or minimum of 15 to, you can say, 40% by the weight of the cement, so that much amount is going to be reduced from the environment. So if we are getting the minimum replacement of 15% and maximum by 40%, then one can save for 225 million tons and up to 600 million tons of the carbon dioxide from the environment. So the analysis of the results, overall, what is going to happen, that we are going to overall save the cost, as well as we are going to cut down the reduction of the carbon dioxide in the environment. So 4 to 6% of the, you can say, economy is going to reduce by this very of the reduction in the carbon dioxide emissions. The performance, next is the performance of any of the mortar mix can be judged by using the compressive strength values, because this is, I told you, one of the basic criteria. So another part is to check that the durability aspect we have not checked. So this is ongoing part. So we'll be focusing on that. Then one of the key issues is that we are lagging. Indian government is lagging about how much of the standard guidelines available for replacement of these very of clinkers or that very of the byproducts with the Portland cement. So another challenge is the availability of these very of the materials, as there are long distance of the transportation. So we are looking into this part. Also, despite neglecting the carbon dioxide emission during transportation, the current study offers the encouraging results, as one part has been found to be successful. So coming on to finally the conclusion. So supplementing the cement and the pozzolans, enhancing the binding properties, and generally considered a decent option for achieving the desired quality and the toughness, as the results, experimental results have shown. Now the carbon dioxide reduction is also possible, as we have replaced about certain specific amount, that is from starting from 20% and goes up to 40%. So ultimately it is going to cut down the CO2 from the environment. Then the blending mortars are suggested for those very of the minor engineering works where mechanical strength is not one of the you can say deciding criteria. So Indian cement industries also has moved from using the conventional materials to the new materials by using this very of the blended options. Finally, the blended cement made with industrial or agriculture byproducts can successfully replace the limestone clinkers. So clinkers are basically the portion in the cement which create a lot of carbon dioxide during the processing. So these materials are having ample chemical composition that they are successfully replaced. So contribution about carbon dioxide reduction is 15 to 20% minimum. That is the for sure. And the Indian government is also promoting that very of the sustainable options for last 20 to 30 years. And using of these blended mortars in a good throw, and several goals have also been set, but for curtailing that very of the carbon dioxide emissions from the Indian cement industry. The basic drawback is that this is not the only approach, because this approach needs the contribution from the private sector as well as from the government sector. So this is the initial phase of the research part. So that's it from my side. Thank you. Namaste.
Thank you very much, Navdeep, for this very interesting presentation. And maybe I just have a starting question. So you said yourself, this is an experimental approach and you need the support of government and also the private and public sector. So here in Europe, we see that we have very strict standards and norms to the usage of cement or concrete in the building sector. Do you see a similar restriction to the use or the large scale use of these new kind of cement in India, or how is the situation there? What would be your presumed barrier for the large scale market introduction?
Thank you, Andrea, for the question. So I just want to clear that there are very harsh restrictions in India also, because people in India, they are trying to adopt the new technologies very hard. So they are already strict to the conventional system. So once the new systems are going to, it's very tough to convince the people as well as the government officials to implement such kind of the products. So restrictions are there in India.
Okay, thank you very much. Simone, do you have a
Yes, I just a question from Matthias regarding the availability of the materials. Do you think the quantities available in India are enough to the projected cement production. What about the availability? Have you analyzed this point?
I just want to make clear that if I go to the slide number 3, where I have shown the map in that, so there are almost 215 major cement producing plants and about 850 numbers of small producing cement plants. So availability of the material is always there. We have huge amount of the plants which are continuously creating a huge amount of cement. So I have also focused on the plants which are upcoming through the generation. So that's why you can see that this starting from the, you can say, top portion to the bottom portion. So the whole country is having almost 215 large plants. So there is no, you can say, hindrance regarding that of the availability of the materials. Either they are agriculture products or they are the industrial byproducts. Hi Simone, I want I think your mic is off. Yes.
There is an additional question from Joan Rotzen.
Yes,
one concern here is that it might be difficult or possibly costly to ensure quality of the cement concrete when adding byproducts. How can this be handled? This is more or less in the line with the question made by Andrea.
Yeah, this is one of the key challenges, I can say, at this point of time. I will look for this also in the coming, you can see, the research part. I'll add it.
Okay, let me check if any other question on the UVA. Let me look on the, no, seem no one. Okay. I don't remember, we have a couple of minutes, right? So if you want to ask something to Navdeep, otherwise we can move on. So.
Okay, then otherwise we now move on to Matthias. Matthias is a researcher at the Fraunhofer ISI in Karlsruhe, and his research focus is modeling industrial energy demand, fuel switch, and deep decarbonization in the industry sector. And today he will discuss the modeling of CE action impacts in the building sector on the EU cement industry. So Matthias, the floor is yours.
Yes, hello, thank you, Andrea. Happy to be here, and today I want to present you something, a little work we did on modeling circular economy action and the impacts on the building sector in the EU cement industry. Authored is Andrea Herbst, who's also sharing this session, a colleague from Rambol, Sami Porteron, and me. And let me guide you through the agenda. First, we'll have a quick look on our motivation and an overview of what we did. Then we go into the model structure, the model we built to answer our questions. And last, we have some insights to share with you. But first, to give you some context, who we are and what you can expect. First, our research group is based at Fraunhofer ISI in Germany, and we work on the decarbonization of the industry sector. To this end, we investigate energy demand in the industry sector, both on the national level, but also on the EU 28 level. We use large simulation models. The most important, at least from my perspective, is the forecast energy model. You can find the homepage on the slide. And we are also doing some dedicated studies on individual subsectors where we don't apply our models, but use other means of research and often develop individual models, smaller ones. In this project, we work with researchers from Rambol and the Ecologic Institute. And what I will present you today is the project we worked on for the European Environment Agency, in which we investigate the potential to reduce greenhouse gas emissions via circular economy actions in the building sector. You will find a link to the project report that's already published on this slide. First, the cement and steel use, we've heard this today, that's no question about it. in the building sector is an important cause for greenhouse gas emissions. So our motivation is that these emission-intensive materials, for example, cement, there's a typo there, it's 0.6 ton CO2 per ton cement in Europe, and steel, about 1.4 ton CO2 per ton, that are used in the building sector. These materials, we need to keep track of them and know how they are used. On the other hand, there are some knowledge gaps regarding the material embedded emissions and the potential impacts of circular economy actions. Short here, CEA, we'll use this to some degree. And what we now want to do, that's our goal on this project, and what I want to convey to you today is that we created a model, a flow model for building materials, and to see how it is produced, how it is used, and where we can do something about it. Include specific entry points for these circular economy actions. We want to consider how these actions interact and how they impact each other. And finally, we want to quantify selected circular economy actions. Now, the goal 2 and 4 have been achieved, we believe, at least, and I hope you agree after I've showed you what we've done. And what we can see here, yes, we have some nice picture of the potential for selected circular economy actions. Starting from the top left, we have the product design, then top right, production process, consumption models, and demolition and waste management. And by this, we follow the entire life cycle of the product and the building and the material. And what we can see that there are some important actions like in the production process, innovative cement types, replacement of cement by timber, for example, and the demolition and waste management, the reuse of structural steel is very important, and so on. So we quantified all of this, and that's all very nice and well, but today I want to give some love to the material flow model and the interaction. And that's what we are doing now. You here on this slide, you see a figure of the model, and the model is built around available sources, and it does reveal some interesting challenges. First, let me have a look at the sources. Our main source for the clinker production process is the GNR project. That's a website from the Global Cement and Concrete Association. It's highly useful. I could recommend it to anyone working on clinker and cement. It's really good because it has data on production of clinker and cement and the end of the energy use in clinker production, not only for individual countries, but also for example, EU28 and for the world. We use these data mainly for the production of clinker, right? It's green highlighted in the model. Then we supplement this data with data from the national associations. Those are usually incomplete. Some have more focus on energy use, some on material use. What we noted is that the type of use, what we can see here on the right side, the concrete use in residential, non-residential and infrastructure sector is the least well covered of all. I would like to highlight, because Timo's here, of course, the great data you can receive from Spain. The National Association has really great yearly balances of production and energy consumption, and also the data from Germany is very valuable. And finally, we had some minor own calculations, for example, of the process emissions, which is basically just a balance of the kiln, input, output, and then the rest is emissions, and the use of water and aggregates. Now, the challenges, as I've mentioned, we have some incomplete data for some countries, especially regarding raw material and the concrete use. We are currently investigating how to integrate innovative processes that, for example, do not use the rotary kiln anymore, how to include this in the structure. And lastly, and that's what I'm going for now, is the interaction, of course, of circular economy actions. There we are. And now bear with me. It looks a lot, but well, it is a lot. Maybe we can do it. What we can see here is on the y-axis the amount of emissions in the EU 28. It's based on 2015. And on the x-axis, you can see several circular economy actions. I know you can't read them now, but these pictures are in our paper and in the report. So it's a waterfall diagram. So when you go from left to right, you see the individual actions, and combined, you see the emission reduction potential. Now, to read an example of these interactions, in blue we have here the action to use the space in the building more efficiently, which means you have to build less buildings, of course. And in green, we have the action to reduce the clinker share in cement, for example, by substitute materials, as we've heard from Navdeep. Now, it's clear that when you do both, that the combined effect is lower, because you're saving the use of a material that has a lower emission factor than before. And now the question is how to allocate this combined effect. In the top case, we assigned the complete savings to the green actions, and the additional savings that occur when you enter this action to the blue savings. And when you do this for all savings together, we can see that for the manufacturing phase on the top part of the figure, you have almost 75% of the savings in the manufacturing phase, and only 25% in the end-use phase. When you turn this around, the order of calculation, that you assign the complete savings to the blue actions, and only the additional savings to the manufacturing phase, the picture changes, and suddenly manufacturing phase and end-use phase are equivalent. So our conclusion from this is that it's important to allocate these interactions correctly, or at least when there's no correct or no wrong way to do it, to make it transparent, because this may very well change the conclusions you draw from your study. That's it. I'm just going to summarize everything. I hope I'm a little bit on time. The modeling of circular economy action impacts the building sector and the EU cement industry. Our motivation was that cement and steel use in the building sector is an important cause for greenhouse gas emissions. Our approach was that we built the model around available sources, and we've seen that it reveals some challenges. Major insight is that the interactions of circular economy actions may influence the conclusions and the policy recommendations, so it's important to consider them. And the outlook, of course, we quantified circular economy actions. How do we get them into the market? How do we actually do this? Finally, contact me with any questions now or later, requests and remarks. Thank you very much for your attention. I'm here for you.
Okay, thank you, Matthias, very much for your presentation. And I already know the paper, but nevertheless, I wanted to ask or summarize. So the conclusion from your paper has been that you cannot say which action is the most preferable one. So in the end, it will be somehow, or has to be somehow, a mix of actions to achieve a near carbon neutral building sector. Or what is the final takeout?
Yeah, I think what we can say that these circular economy actions we investigated are also not enough to reach the complete deep decarbonization. But it's a step one should not omit. It's a very important step. But you are right, we cannot say which of these individual actions is the most important one, because due to this interaction, it really depends how you in which order you calculate the savings, and that's not just a calculation issue. It's a real world issue, because when you want to use less material, that's great. But if you use less material of a low intensity material, what's more important? But I would say yes, you need to do all of them basically.
Okay, thank you very much. So Simone, do we have any additional questions?
No, from UVA, it seems no questions. let's wait some seconds.
Timo has a question.
Okay, Timo, open your mic.
Sorry, I wrote the question to the support. That's why it didn't reach you. No, I'm actually quite curious about cement recycling itself. I mean, it goes a bit beyond your presentation, but to what extent do you consider it likely that cement recycling is actually going to play a major part, because it's so much effort for such a basic material?
Yeah. Well, we included cement recycling as an option, as a circular economy option, and I think it could be relevant. You can see in the paper and also in the figure I presented that in about 60 megatons of concrete is demolished each year according to our estimate, and of this the cement could be reused. There is, to my knowledge, only one technology that is trying to do so as of now, this smart crusher one. I don't know whether they can achieve an economic operation yet. It would, of course, be interesting because you would save these process-related emissions. And even when you decarbonize the energy consumption of cement production, you still have this process-related emissions where you really can't get around, except with CCS. And as Navdeep mentioned, there are reservations against CCS, not unjustified, I would say. So eliminating the problem at the root, basically, and not having to do CCS is, I would say, preferable. And if you can do this by recycling material, that's a great solution. Yeah. But it's economically challenged, as you maybe, yeah.
Thank you, Matthias. We have a couple of questions. What information you collected for each circular economy action, and from which sources you got them?
Yeah, thank you, Felipe. Actually, I would refer you to the report because it's a lot of work that has been done by our partners actually at Ramboll Ecological Institute. There are, if I remember correctly, there are a lot of literature, scientific literature, of course, and also some companies that are trying to get those options in the market. For example, what I just mentioned, smart crusher or innovative cement types, which are not at the moment in the market, in a broad market, but only in very small quantities. And yes, I can't give you a detailed answer now, but it's in the report and in our paper. I believe it's also a list.
Okay, I think that Felipe can have access to it. Any other question from the audience? In WUVA, not any additional one. Again, I think that we can move on, and of course we will have discussion at the end with additional questions.
Thank you.
Okay, thank you very much. Then we will move on to Ida, who is a PhD student at the Energy Technology Division at Chalmers University of Technology in Göteborg, Sweden. And after working a decade in different international sustainability roles in industry, she's now decided to pursue a position in a very large-scale research program, which is called Mistra Carbon Exit. And today she will present a roadmap for climate transition in the building and construction industry. So Ida, the floor is yours.
Thank you, Andrea. First, I will probably, I wanted to say to Timo, thank you for highlighting your work on the cement industry. Actually, today I won't really present specifically into the cement, but the work that I'm presenting today is based on the work into the cement industry. So what I will present today, go back, is a roadmap for a climate transition of the building and construction industry in Sweden, which is based partly on supply chain analysis of the steel and cement industries. So the basis for this is really from the Swedish quite ambitious target set of reaching net zero emissions by 2045. So we have looked into how the building and construction industry looks today, and what will be possible abatement options along the supply chain. And currently we see that the manufacturing and transport of construction materials together with construction process is responsible for about 20% of Swedish CO2 emissions. And actually what we see is that concrete or cement and steel together with diesel use in material transport and construction processes are responsible for about 70% of those emissions. And what we found in our work, which is also what Matthias highlighted, is that when you look at the material and energy flows, there are quite some gaps in terms of the availability of literature. So we've used a bottom-up process to get the material and energy flows, which is based on LCA studies. And what we then did is quite an extensive literature review looking at abatement options for these key materials and activities, and looking at both what do we see as abatement options that are available today, and also what do we see could be available up until 2045. And then to kind of test these, we have put to test how the impact of what these supply chain abatement options could provide in terms of potential for the entire sector. We have put them together into different pathways, given different abatement focuses. And some examples of some abatement options, which we've already seen here, raised for concrete and cement, is both in terms of clinker substitution, optimization of concrete recipes to use less cement, and also some material substitution into timber. And we also looked at into the longer term in terms of carbon capture, biofuel substitutions with or without electrification. And for steel, we're looking at some biofuel or biomass substitution into the production plant, and in the longer term, electrification of the primary steel production plants with, for example, renewable hydrogen. In construction process and in heavy transports, in addition to optimization of logistics and fleet management, we also looked at biofuel substitution in the short term, combined with hybridization and eventually electrification fuel cells. For other materials, we looked at potential for material substitutions and different types of circularity options. And in the longer term, also looked at electrifying manufacturing plants. And for all of these industries, we looked at cross-industry, we looked at material efficiency options, such as slimming of constructions or structures, some reuse of materials, etc. And also we'll say that along the industry, as you come to electrification, you also get some benefits from electricity system decarbonization. And some just exemplification of the timeline that we've looked at. So we've devised 4 pathways for the building and transport infrastructure construction, which describes different future trajectories of technological developments. And 2 of these have a focus on biofuel combined with carbon capture and storage in the longer term, and 2 have a focus of electrification of the manufacturing plants. And then these 2 of the options also looked at what role the material efficiency measures could play in the low carbon transition. And I would say that the measures and the timelines of these are largely compatible with the EU Commission long-term climate strategy, as well as individual industry roadmaps that have been developed in Sweden within the government initiated initiative Fossils Free Sweden. And then what do we see as a result of this? Well, we see that currently construction of building and transport infrastructure in Sweden uses about 32 terawatts of energy, which is about 8% of total Swedish energy use. And all the pathways demonstrate a reduction in total energy use over time, ranging from about 6 to 19% to 2030, and 16 to 37% to 2045. And when comparing the different pathways, we see lower energy use for the electrification pathways, mainly a result of lowered energy requirements for electric propulsion, and also looking at the energy penalty for post-combustion capture in cement plants. And regarding, if we look at how the different energy sources are used, we see that the biofuel use, which is currently mainly used in the transport sector in Sweden, as well as in some asphalt, cement, and timber production, they're set to expand, with the overall share increasing from about 15% total energy use at current to 30% in the electrification pathways, and even up to 40% in the biofuel pathways. And the electricity use is almost constant in the biofuel pathways, but doubles in the electrification pathways, reaching a share of around 65% in the electrification pathways. And in terms of material efficiency, we see that a focus on material efficiency has the potential to reduce total energy use by about 20% to 2030, and 10% to 2030, and 20% to 2045 in comparison to the alternative equivalent pathway. In terms of emissions, we actually found in our modeling that all pathways have a potential to reach close to zero emissions in 2045, with emissions reductions ranging from 90 to 94%. And up until 2030, we see emissions reduction potential of over 50%. And as you can see, a lot of these stem from optimization of concrete. So in Sweden, and it's worth noting here, that in the Swedish context, we have generally a low use of alternative binders compared to the European setting. And we also use more cement generally in the concrete recipes. So this potential might be slightly lower in the European context. But we also see a combination of this with energy efficiency measures and other measures in terms of transport and construction equipment being the main sources of emissions reduction potential in the short to medium term. And after 2030, then we have deeper emissions reduction stemming from then, of course, the combination of carbon capture or combined with electrification. And what's interesting, I'll say that we see that a focus on material efficiency, and of course, I would also note here that we also find, just like Matthias did, that it depends a little bit on where did the material efficiency measures come? Do you put them on the end or do you put them on before? In this modeling, we have, of course, you can't see it here where we allocated it, but we allocated it to I would say, how much material is used, and then the material efficiency measures first, like we did in the second option, Matthias. And we found that in that the focus on material efficiency can provide additional reductions, particularly in the short term, which is then a positive measures before we can reach the really deep decarbonisation measures. And if we look at the cumulative emissions from 2020 to 2045, we see that a focus on material efficiency could reduce the cumulative CO2 emissions released by about 10% compared to corresponding pathways. And finally, I would say that a key takeaway from this work is the importance of simultaneously focusing on both short and long-term measures. So by that, I mean that the pursuit of sort of low-hanging fruit can't be an excuse for not acting on creating the foundation for high-cost, long lead-time measures, and vice versa. That the promise of, so to say, zero or low CO2 steel or cement can't be an excuse to act on unlocking the potential for measures that exist already today. And we find that that unlocking the full abatement potential requires not only technological innovation, but also innovations in the policy arena, as well as finding new ways of cooperating, coordinating, and sharing information among the actors in the supply chain. And we also find that which other similar work we find is the importance of support infrastructure. So we need to ensure sufficient availability of sustainable biomass for biofuel, enough renewable electricity, as well as green hydrogen. So strategic planning for key support infrastructure needs to start already now in order to enable these deep abatement measures to be implemented by 2045. So to summarize, I would say that we find that over 50% emissions reductions are possible by 2030 and close to zero emissions by 2045. But this requires increasing efforts on all aspects along the supply chain. So we need to have all abatement measures in place in order to make that happen. And thank you for that. And I will also highlight that you can find all the technical reports that are behind this, which is what Timo showed, and the same with that we have for steel industry on the Mr. Carbon Exit website. Thank you.
Okay, Ida, thank you very much. This was a very interesting presentation on the case of Sweden, and maybe I will just start with one question, and I'm not sure if there is a clear answer to that, but you showed in your 4 pathways more or less 2 directions that are possible. On the one hand side, it's more like CCS in combination with material efficiency, and on the other, it's electrification in combination with material efficiency. So what we know is that Sweden is like a first mover in hydrogen use for the steel industry, but of course, what kind of hydrogen will there be used is not yet clear. So it can be hydrogen based on renewables, but it could also be hydrogen based on natural gas. So what we had in discussions with industries, it is that the hope or the danger might be that if this hydrogen, which is used in the economy, is based on natural gas, then this opens the floor for CCS in other industries, for example, the cement industry. And my question would be, which kind of scenario do you see at the current stage more probable, the CCS case for cement in Sweden, or would it still be electrification?
I think that's a good question. When we talked with this Swedish cement producer, they are still open for alternatives, and I think there's a bit of a waiting game looking at the Norwegian pilot case where they are doing a full-scale carbon capture, and to seeing how well that works and to seeing what kind of options there are, as well as at the same time trying to focus on, because as Timo said before, electrification is an area that hasn't really been worked on that much so far in the cement industry, but they are looking at it quite extensively because it opens up for about 100% carbon capture because you still need to combine it in order to get the process emissions, but it simplifies the carbon capture process. So it is interesting, especially for Sweden, which has quite large potential for renewable electricity. And I would say that so far, I think it depends a little bit on how the situation looks like in terms of how much renewable electricity potential do you have. Do you see, like in terms of the country, is it easier? Would it be easier to go for a solution where you can get to maybe 90% carbon capture without electrification, or do you have potential for electrification and are able to look at it to make that feasible? Then electrification is probably a better option.
Okay, thank you very much. So Simone, do we have any additional questions?
Just one very closely related to the discussion of carbon capture and storage. Since it's made by Matthias, he said that you can reach close to zero by 2045 emission. Isn't it without any carbon capture storage? And how is it possible?
No, this is all with carbon capture. So even the electrification pathways uses carbon capture where that is needed. So in terms of the cement plant, for example, where you will not be able to get to 100% otherwise. So it's more about the focus. Is the focus more on looking at implementing or substituting towards biofuels, or is the focus more on electrification?
Okay, thank you. So quite understandable that you are not just looking at one single action, but jointly. No, any other question? I think that we can go to the presentation, the next presentation.
Okay, then thank you again, Ida.
Thank you.
Our next presenter is Søren Nyborg Rasmussen. He is Senior Manager at ROCKWOOL Technical Insulation, and Søren is a chemical engineer, and he has more than 30 years of experience from the global marine, offshore and process industries, specializing in insulation and protective coatings. And today Søren will give a short introduction to how to insulate industry and how the insulation industry is working with sustainability.
Thank you very much. Yeah, my paper today have a little bit different angle than the previous papers, but still we'll be in the same ball game. I would like to start up with a few words about the use of insulation in the industry first, because at least there's an interesting angle in that respect. Because what the current status is today is that insulation specifications used today also on new installations, they are pretty old because it's a lot of copy paste from the past. People are focusing on surface temperatures because of safety, so people do not get a burn, but they do not really focus on energy efficiency when they are making the specifications for the new installations. This also means that in the industries, and that is across industries, different types of industries, then there is a big potential in terms of obtaining energy efficiencies and also reducing carbon dioxide emissions. And it is because, yeah, as we probably all recognize, the most sustainable energy, that's the one that we don't use. Just a few examples on that is that we can see that if we are saving a kilowatt hour by the use of insulation, even insulation that, as Ida was mentioning, because it was in one of the charts in the previous presentations, that also generates carbon dioxide when it is produced. But even when we are using that type of insulation, then by saving the energy, then we have a much less or much smaller carbon footprint than when we have to generate the electricity or the energy first, even by solar or wind. Good. Yeah, and especially in the industry, when you are working with high temperature equipment, then there are huge benefits in insulating the equipment. You can save quite a lot of money, of course, but also carbon emissions by using insulation on hot equipment. Just as an example, you can say the small part of the ROCKWOOL organization that I'm representing, which is called ROCKWOOL Technical Insulation. We are supplying insulation for the industry, and we are of course just one supplier of industrial insulations. And what we are supplying in 1 year, over the lifetime of that year, over the lifetime of that insulation, then it's going to save the energy that the country of Germany is using in 1 year. So it's a huge amount of energy that is being used in the industry, and there's a lot of potential of doing something about it. So insulation, that's great, and it's a great way of saving energy and also reducing the carbon footprint. But that doesn't mean that we as industry cannot improve, because when we are producing our insulation materials, for example, in our case, we are producing stone wool. Then we are melting stone. We are using a lot of energy to melt the stone. We are creating emissions, lots of carbon dioxide emissions, and we are also generating waste. And also, when you consider the volume of our products, then there's also some questions and marks about what should you do with this material, this voluminous products, when at the end of the lifetime of that material. So we definitely have challenges, and we definitely have areas where we can also improve in terms of our industry. And that's also why, at least from our company, we are trying to use the global goals in order not only to drive our product developments, which we are, but also in order to optimize our own operation and looking into how can we also as a company optimize our own operation in terms of the sustainability goals. I will pick a few of these sustainability goals and then explain what it is that we are doing as an insulation company to improve in these areas. So one key target, obviously, as all the previous presenters were also addressing, was about the energy consumption and especially the carbon footprint. And this is an area where we are trying to improve a lot, both in our existing factories, but also when we are making new investments in how can we actually improve the way we are doing things so that we are minimizing our energy consumption and also improving carbon footprint. So in the factories today, we are of course monitoring our energy consumption. We are monitoring our carbon emissions. We are setting up targets on the factory floors, work and what we need to achieve. We are also sharing best practice between our different factories so that we can learn from the good cases from different factories. But specifically today, then I will also talk about two of the other things that we are doing, because we are, from a financial point of view, we are looking a little bit differently at investments into our factories than we did in the past. So now it's not just a matter of, you can say, payback time, getting the most out of it. Of course, money is still important, but we're also looking at how can new investment improve, you can say, our total footprint? How can we save energy? How can we reduce our carbon footprint? I will come back to some examples on that later on. And then I mentioned that there's a lot of challenges in the industry as general, that insulation specifications can be upgraded, because in many cases it's surface temperatures that has been the focus, ensuring that you are in compliance with the regulations for your operation. And big surprise, it is also the same is also the case in the ROCKWOOL factories and insulation factories. When we have made the factories initially, we didn't focus so much on insulation. We focused on the cost of the factory. We focused on the cost of the material that came out in the other end. We did not focus on optimizing insulation. Likewise, when we are doing maintenance in our factories, we are not focusing so much on energy efficiency, or did not focus so much on energy efficiency. We focused more on having the operation running, getting some stone wool insulation out of the factory. One of the tools that we are promoting in the industry is a tool called TipCheck. It's an energy audit where insulation specialists are coming out to factories and doing energy audits of the factories, simply measuring, you can say, the amount of energy loss from surfaces and mapping out a complete plant in terms of where can we improve on energy efficiency. We applied this principle on our own factories, and because we thought that, okay, we also need to take our own medicine, and it's very clear that there are lots of potential also in the stone wool factories for improving on the insulation and improving on energy efficiency, and definitely also in our carbon emissions. This is just one example that I have here on the slide. I'm not going to in details on this, but there are plenty of those examples in the industry where you can go out, you can find equipment, you can upgrade the insulation of the equipment, and from day one you can start saving, and you can have quite short payback times. In this case, with the example here, the payback time was 2 years when we implemented this upgrade. So in the industry, also in the insulation industry, we can go in and look at the existing facilities, and we can upgrade and reduce our emissions. I also mentioned that it was also possible to look at, you can say, the way we are financing new equipment, and this is also one of the things that we are doing. We are investing in new technologies, and by changing, for example, our melting technology to electric melters, then we can reduce significantly the carbon dioxide emissions. These are huge investments. Smaller investments are if we change from coal or coke to gas, then we can also reduce our emissions. Right now, our factory in Moss, 2 hours drive north of Gothenburg, we are actually implementing a new melting technology, going for electrification, because in Norway we can get hydropower, so we can get renewable energy. And here,
Okay, at least I cannot hear Søren anymore.
sorry, that was my fault.
Okay.
So we can save significantly on the carbon emissions. Okay, another challenge, that is insulation waste. This is here both in our production. We are generating waste. We can recycle that, but also the insulation that our customers are using, the cut-off waste during the installation, but also when they are dismantling after end of use, we are actually able to take that insulation back and recycle it. So this is technology we have, something we can do. We just need to upgrade some of our factories to be able to do it more, and we need to, of course, also build the infrastructure around it. But it is something that we are working on, and we are implementing in country by country, that we can take back the old insulation. We have done it. We have a lot of experience with it. This is an example from the UK with the power plant, where we took back we're taking back all the old insulation, making it into new insulation in conjunction with refurbishments. It's a clear target from ROCKWOOL that eventually we want to be able to take back all the old stone wool and make that into new ROCKWOOL. For us, we work very much with the global goals, and we have clear sustainability targets in our company. We have targets that we are also reporting back to our investors in quarterly investor calls, and then we are also issuing a sustainability report. In order to report, just like we are doing on the finance, we are also reporting on our improvements in this area. So I think I ran over a little bit on time, but I hope that that it was okay. If you want to learn more about how ROCKWOOL is working on sustainability, then I recommend that you download our sustainability report. Otherwise, I'm also open for questions now. Thank you.
Thank you very much, Søren, for this very interesting presentation. And I think I will just start with one question. And I just wanted to ask, yeah, now if you do this recycled insulation wool, of course, this means you have more efforts, but what does this reflect on the price? Is this product then more expensive than a standard insulation rock wool you can buy somewhere and the buyer has to decide if he wants to do something for the environment, or are costs and benefits more, I don't know, equal?
Yeah, it's a good question, and I understand what you mean. It's actually not the buyer who is affected here. It will be, you can say, indirectly it is. It will be our customers who will have you can say, the choice. Do I want to send the used insulation for landfill, which a lot of people have done in the past, or do I want to pay maybe a little bit more? In the future, it might not be more, might be less, and send it back to ROCKWOOL where it can be recycled. So that's basically the challenge. And we have a number of customers who are, you can say, choosing, we want to send it back, and then we are reworking it into new stone wool. So the new material is no different from the material that is coming from, that's being made from stone.
And do you see the need for public incentives that more customers will choose this option, or do you think it's just takes some time?
I think it will come automatically because you can say waste is becoming more expensive everywhere, and especially waste that goes for landfill. That is becoming more expensive, and so that's one part of it. The other part is also that it's not only ROCKWOOL who are making these sustainability reports. Other companies are doing the same and sending waste, and it could be used insulation, to landfill. Does not look good on a sustainability account. So there are different drivers that definitely is going in the direction of more recycling going forward.
Okay, thank you very much. Simone, do we have any additional questions?
Yes, we have a couple of questions, both from Matthias. First of all, a very precise question regarding the total emission in terms of CO2 for each ton of product. So
yeah, and I apologize that I cannot say that, but that is something you can read in the sustainability report, because that is one of the things that are being reported. But it's clear when you are melting stone, we are melting stone at 1,500 degrees C. In most of the factories, they're using coal or coke as main fuels. So it is generating emissions, carbon dioxide emissions, for sure. Okay. And we are one of the industries that are you can say emitting a lot of carbon dioxide.
Okay. When you put in your graph the numbers regarding different measure, different or comparing insulation with others, let me say, renewable energy sources, I can imagine that if we look at industrial insulation, the story is completely different from the building insulation, since temperature there are completely different. So if we are thinking about, I don't know, 10 centimeters thick on a wall, on a pipe with 200 degrees compared to 10 centimeters for a wall in a stone, in a house, will be completely different. So the number comes from building or from industry? It's an average.
Yeah, it is an average for ROCKWOOL, and I believe that these numbers are from buildings actually, because that's where most of the insulation is going. But what you can say is, as a rule of thumb, is that the insulation that is used for buildings, there you get kind of the carbon dioxide that you are generating during the production. You can say that's saved 50 times during the lifetime of the insulation on the building. For the industry, you can say a rule of thumb is the same figure is like 10,000. So yes, you're absolutely right. High temperature equipment, that's where you get significantly more benefit of the insulation. But interesting enough, now we are talking about that, is that on my house, I have like on my roof 350 millimeters of insulation. The majority of the industrial insulation for high temper equipment, I mean, is using significantly less thickness. So it's also like you can say there's room for improvement. But unlike for the buildings, you can say where we have building codes that are very strict insulation standards, then for the industry, it's not like that. It's for the it's up to the individual company how they want to spend their money. You can say.
Okay, just last question: how often the insulation should be replaced?
It depends. I mean, a lot of the insulation that we are supplying, for example, for buildings, but it could also be for lower temperature equipment. That insulation will typically be there for the lifetime of the structure. So you don't need to remove it or replace it because it doesn't age or more than you can say the construction. When it comes to high temperature equipment, then maybe it's every 10-15 years you need to replace it.
Okay, thank you. Andrea, you can close the session,
Yeah,
I think.
okay. Thank you very much for this very interesting session. Especially thank you very much to our presenters for whom it was not easy with this new format. So you really did a great job. And I think this was a really interesting session on the multidimensional problem, how we need to decarbonize also our industry, but also the building sector. We saw different strategies how to achieve this target. And I hope you will stay with us in panel 2 and also join us in the afternoon where we will talk about a little bit more on the geographical aspects and triggers for circularity and decarbonization. And Simone, maybe you also want to add one sentence and then we just...
I would invite everyone to join this session in half an hour. So.
Okay, then thank you very much and hope to see you soon. Bye.
Bye, thanks.
Bye.
Thank you. Thank you very much. Thank you.